Welcome to Quiet Science Journeys. Tonight, imagine the universe like a vast, dark sea foam. The bright filaments are the places where galaxies gather, and between them are enormous quiet hollows wide enough that your mind naturally slows down. In those hollows, there is no tear in reality and no danger. There is simply less, fewer galaxies, fewer luminous signposts, less matter than average. And sometimes, when there is less clutter, the underlying pattern becomes easier to read, the way a calm lake makes the horizon feel sharp and steady. If you are listening while already tired, you do not need to remember details. You do not need to hold on to numbers. Let this be a gentle science-heavy companion, spoken slowly enough that you can release it at any moment. Tonight's idea sounds almost backwards. We are going to learn about the universe by studying its emptiest places. Those emptiest places have a name: cosmic voids. They are regions inside the cosmic web where galaxies are sparse. They can span tens to hundreds of megaparsecs, meaning hundreds of millions of light years. You do not need to carry the scale in your head. Just keep the feeling that these are quiet volumes large enough for light to take a very long time to cross. And there is a telescope designed for this kind of work. The Nancy Grace Roman Space Telescope, often called Roman. Roman is not built for a single dramatic close-up. It is built for patient surveying. It looks wide. It maps carefully. It repeats. It turns large pieces of sky into a clean, statistical picture where structures as broad and subtle as cosmic voids can finally speak clearly. Here is the steady tone we will keep tonight. We will not chase loud claims. We will not try to force the universe into a headline. We will follow a method that measures, labels uncertainty, and leaves the rest resting quietly on the shelf. Our thesis for tonight can be held in one calm sentence. Cosmic voids are so underdense that the history of cosmic expansion can be easier to read in their statistics, and Roman is designed to measure those statistics across a wide and deep survey of the sky. To get there, we will take a slow route with three simple stages. First, we will meet cosmic voids as real structures, not as nothingness. A void is not empty. It is a measurable kind of sparse, shaped by gravity, and by the way matter flows through the cosmic web. Second, we will meet Roman as a tool, not as a list of parts, but as a reason. Wide field, deep reach, stable measurements, and enough galaxies to turn emptiness into data. Third, we will connect that data to the quiet question behind it. What does the pattern of voids tell us about the way the universe expands over time, and why does that connect to what scientists call dark energy? Not as a substance you can hold, but as a name for a behavior we can measure. And if you fall asleep anywhere along the way, that is perfectly fine. There is nothing to complete, no test at the end. Just a night journey, slow and steady. So let's begin with the simplest picture. A dark web of galaxies and a wide, quiet hollow between its threads, and the gentle idea that even absence can leave a measurable signature in light. Cosmic voids can sound like a strange focus at first, because the mind expects science to point at something bright. A star, a galaxy, a planet with a hard edge. But voids invite a different kind of attention. They ask us to look for structure where the structure is made of absence. So for this first stage, we will build one calm picture and keep returning to it. The universe is not a random sprinkling of galaxies. On the largest scales, it forms a pattern often called the cosmic web. There are filaments where matter gathers. There are walls and clusters where gravity has done a long, slow job of pulling things together. And between those denser regions are the voids, the underfilled volumes that give the web its open breathing space. If you like a gentle image, imagine a snowfall seen from above at night. In some places, the wind piles snow into bright ridges. In other places, the wind scours the ground, leaving wider, smoother patches. The scoured patches are not nothing. They are part of the same landscape. They have a shape. They have boundaries defined by where the snow chose to gather instead. Voids are like that. They are part of the landscape of matter. When astronomers say a region is a void, they are not pointing to an empty box. They are describing a region that is underdense compared to the cosmic average. Fewer galaxies. Less matter than you would expect if you took a random slice of the universe. It is a statistical idea, but it becomes a physical one because gravity turns statistics into shape over time. Here is one layer of mechanism kept soft and simple. Early in the universe, matter was distributed almost evenly with tiny variations. Slightly denser patches had slightly stronger gravity. Over billions of years, those slightly denser patches pulled in more matter and became denser still. Meanwhile, the regions that started out slightly underdense lost their matter to the growing filaments and clusters around them. Those regions became emptier over time, not because something removed matter on purpose, but because matter flowed where gravity made it easiest to gather. A void is in a sense a memory of that flow. If you let your mind settle into that picture, you can feel why voids are such a clean place to learn. In a dense cluster, everything is complicated. Galaxies collide, gas shocks, star formation flares, black holes feed. The physics becomes rich, but also noisy. In a void, many of those messy nonlinear processes are quieter. The region is dominated by the large-scale story expansion gravity and the slow redistribution of matter. That does not mean voids are perfectly simple. It only means the foreground clutter is thinner, so certain background patterns can stand out. Now, it helps to name one more subtle point. A void is not defined by one single galaxy being missing. It is defined by the pattern across an enormous volume. Some voids contain a few galaxies. Some contain faint small galaxies that are harder to detect. Some are laced with thin filaments. The key is that as a region, they are sparse compared to the average. And because the idea is statistical, the real strength comes from numbers. Not one void, but thousands. Not one boundary, but a population of boundaries that can be compared. This is where the phrase turning emptiness into data becomes more than poetry. To turn emptiness into data, you need to do two things. First, you need tracers. Galaxies are the most common tracers because they are the lights we can see across immense distances. When we map where galaxies are, we can infer where matter tends to be. Not perfectly, but well enough to identify the broad structure. Second, you need a rule for identifying voids. In practice, astronomers use algorithms that search the galaxy distribution for regions that are unusually underdense, often by looking for basins in the density field, or by finding large empty spheres that can be packed into the map. Different methods emphasize different features. Some find many small voids. Some find fewer larger ones. And that is not a problem. It is part of the discipline. In good science, you do not pretend one definition is the only definition. You test multiple definitions and look for results that remain stable across methods. That stability is one of the quiet comforts of this field. The truth does not need a single perfect lens. It can be approached through several imperfect lenses that agree on the same underlying shape. Now let's make this stage feel even more tangible by talking about what we can measure about a void. The simplest measurement is size. How wide is the underdense region? How far does it extend before the density rises again into the filaments and walls? But size is not the whole story. Two voids can have the same diameter and still be very different inside. Some voids have a gentle density profile, gradually rising toward the edges. Some have sharper boundaries. Some are elongated, stretched by the surrounding structure. Some are more spherical. So when scientists use voids to learn about cosmology, they often rely on statistics that describe a whole population. They look at how many voids of different sizes exist. They look at the average density profile as a function of radius. They look at how voids are distributed relative to each other. They look at how voids correlate with the cosmic web around them. And each of these measurements is a way of reading a page in the same long book, the book of how matter and space have evolved together. Here is a gentle pause. Imagine a wide, dark valley. It is not empty. It has air. It has dust. It has a shape carved by rain and time. The valley is defined by what stands around it, but it also defines the landscape by giving the surrounding ridges their context. That is what a cosmic void does for the universe. It is the negative space that reveals the sculpture. Now, we come to the question that makes voids truly powerful for Roman's future work. Why do voids connect to cosmic expansion? We will keep it to one layer. Cosmic expansion sets the overall scale of distances in the universe over time. Gravity works against expansion by pulling matter together. The shape and growth of the cosmic web are the result of that long negotiation, expansion, stretching space, gravity, gathering matter, and dark energy in our current best model, accelerating expansion at late times. Voids sit at an interesting intersection of these effects. Because they are underdense, they are less dominated by strong gravitational collapse. Their evolution can be more directly tied to the expansion history and to the way large-scale structure grows. That means certain void statistics can respond measurably to different cosmological models, not in a dramatic, instantaneous way, in a slow, statistical way that suits surveying. This is why you may hear people say that voids can be a clean probe. In low-density environments, the messy small-scale physics can be less dominant, allowing some cosmological signatures to stand out more clearly in the statistics. And there is another quiet advantage. Voids are large, enormously large. And when you are measuring cosmology, large structures matter because they reduce sensitivity to small local irregularities. A single galaxy can have quirks. A single cluster can have complexities. A void population across a huge volume is closer to the true average behavior of the universe. So this first stage can be held in a simple progression. Gravity gathers matter into filaments and clusters. The spaces between those structures become underdense. Those underdense regions form voids with measurable sizes and shapes. A population of voids carries information about the expansion history and the growth of structure. And because it is statistical, the method becomes stronger as your map becomes wider and deeper. That last line is the bridge into Roman. But before we cross that bridge, let's rest inside the present image one more time. Picture a map of a coastline at night. You do not understand the coastline only by looking at the land. You also understand it by looking at the sea. The sea defines the land's edge. The land defines the sea's hollows. Together, they make one shape. In cosmic maps, the bright filaments and clusters are the land. The voids are the sea. And when you map both well, you begin to see the true geometry of the whole landscape. Now, there is one more piece of quiet discipline that belongs in this stage, because it will keep the rest of the video grounded and calm. We are not trying to find a void the way we find a planet. We are trying to characterize a population of voids. That means our conclusions will not come from one dramatic example. They will come from patterns that remain when you average over many examples. This is the kind of science that does not demand excitement. It rewards patience. So when we say Roman will teach us about voids, we do not mean Roman will show us a single famous void up close like a portrait. We mean Roman will survey wide enough and deep enough that voids become a reliable statistical instrument, like a set of many measurements that agree. And this is a calm kind of power, because it lets the universe speak in its own steady language, large numbers, clear trends, slowly shrinking uncertainty. Let's end this stage with a small, sleep-friendly summary, like placing 3 smooth stones on a table. First stone. A cosmic void is not nothing. It is an underdense region shaped by gravity and by the cosmic web. Second stone, voids have measurable properties. Size, shape, and density profiles studied most meaningfully as a population. Third stone. Because voids are large and comparatively quiet environments, their statistics can connect to the universe's expansion history in a clean, testable way. You do not need to hold more than that. In the next stage, we will meet the tool built for this kind of work. A telescope that is less like a spotlight and more like a wide, steady lantern. The Roman Space Telescope and the reason wide field surveys are exactly what cosmic voids have been waiting for. When you think about a telescope, it is natural to imagine a single narrow gaze, one target, one deep stare, one dramatic image, as if the universe were a portrait studio. Roman is a different kind of telescope. Roman is built for surveying, for mapping, for returning again and again to large patches of sky until the noise fades and the structure remains. It is less like a spotlight and more like a wide, steady lantern moving slowly across a landscape. And that matters because cosmic voids are not small objects. They are not found by zooming in. They are found by stepping back far enough that you can see the pattern, and by collecting enough data that the pattern becomes statistically trustworthy. So in this stage, we are going to do something simple. We are going to meet Roman in the way that best fits this story. not as a list of parts, not as a parade of acronyms, but as a reason. A reason why this particular observatory is so well matched to the science of emptiness. Begin with the most important idea wide field. To map voids, you need two things at the same time. You need breadth, because the cosmic web is vast. And you need depth, because the galaxies that trace structure are spread across distance, and many of them are faint. A shallow map is like a map drawn with too few street lights. You can see a few bright intersections, but you miss the subtle neighborhood lines that connect them. Roman's wide field survey ability is designed to solve that. It is meant to cover large areas of sky, efficiently gathering consistent measurements across a huge volume. That is the basic ingredient cosmic voids have been waiting for. Now let your mind hold an image. Imagine you are trying to understand a forest from the air at night. If you only look at one small clearing, you learn almost nothing about the forest's shape. If you take a wide aerial sweep, you begin to see where the trees cluster, where the valleys open, where the river cuts through. Voids are those open valleys. You need the wide sweep to see them as part of a coherent terrain. Roman is built to give that sweep. Now you might wonder what kind of light Roman uses and why that matters. Roman is designed to work in the near-infrared and visible light in a way that is especially useful for deep surveys of galaxies. Near-infrared observations help because as you look farther out into the universe, the light from distant galaxies is shifted toward longer wavelengths. In a soft, quiet sense, distance changes color. The more the universe expands along the path of the light, the more the light's wavelengths stretch. You do not need to memorize the physics of redshift tonight. You only need the gentle consequence to map structure far away. You want instruments that can see the faint, stretched light of distant galaxies well. And when you combine that with a wide survey, you begin to understand why Roman becomes a perfect partner for void science. A wide field gives you volume. Sensitive measurements give you depth. Together, volume and depth create a dense enough map of galaxy positions to identify underdense regions reliably. And this brings us to a calm but crucial principle. Roman does not need to take the most detailed image of any single galaxy for void work. It needs to take consistent, high-quality measurements of a very large number of galaxies. For void science, the unit of value is not the single photograph. The unit of value is the statistical map. This is why survey telescopes have a different kind of beauty. Their beauty is not only in individual images. Their beauty is in the quiet accumulation of data. Now, there is another reason Roman matters here, and it is about stability. When you are doing large surveys, you want the measurement system to behave consistently. You want the same sky observed in the same way with well-understood calibration, so that differences in the data reflect the sky, not the instrument. Roman's mission design emphasizes that kind of stability and repeatability. That repeatability is the gentle heart of all mapping science. If you return to the same region of sky again and again with careful control and calibration, the random fluctuations average down. The map becomes cleaner. And when the map becomes cleaner, void finding becomes more robust. So you can think of Roman's job as a slow clarification, not a sudden reveal. A slow clarification. Now, we can let ourselves take one small step into how a void map is actually built. To identify voids, astronomers begin with a catalog of galaxies, a list of positions on the sky, and ideally some sense of distance. When you add distance to sky position, you can turn a flat map into a layered map. Not perfectly three-dimensional in the way your hands understand a room, but three-dimensional in the way statistics understand volume. Roman surveys are designed to create the kind of catalogs that are large, uniform, and deep enough to support this kind of volume mapping. And here is a soothing detail. Even if the distance to each galaxy is not perfect, a large survey can still be powerful because the strength comes from the ensemble, from the average behavior over many galaxies. When you are measuring large-scale structure, small errors can wash out while large coherent patterns remain, especially when you have a great many tracers and a very large volume. This is one of the kindest truths in astronomy. You do not always need perfection. You need enough data and enough honesty about uncertainty for the patterns to become reliable. Now, Roman is also known for another capability, the coronagraph, which is designed for high contrast imaging of exoplanet systems. That is a beautiful instrument in its own right. But for our purpose tonight, we will keep our focus on Roman's wide field survey role, because cosmic voids are a survey science. The coronagraph is like a fine needle. The wide field survey instrument is like a broad brush. Voids are painted with the broad brush, so let's stay with that brush for a moment. A broad brush does not paint detail in one stroke. It paints the background. It lays the field. It shows you where the structure is and where it is not. And once you have that field, you can begin to ask the cosmological questions. Now, here is where Roman becomes especially exciting in a quiet, method-driven way. Roman is not working alone. In modern cosmology, the most confident results usually come from combining multiple lines of evidence, different surveys, different instruments, different techniques. The goal is not to create a single perfect measure. The goal is to cross-check the universe from many angles, looking for agreement, and also looking for places where the story does not match. Voids contribute a distinct angle. They turn the underdense regions into a probe, a measurement channel that complements other channels. In the same way that you might measure a room's temperature with two thermometers and trust the reading more when they agree, cosmology trusts its conclusions more when independent methods converge. Roman's wide surveys are designed to strengthen that convergence, and when methods do not converge, that is not a failure. That is information. It tells us where we need to look again, refine assumptions, or improve the model. So Roman's contribution is not only data, it is disciplined comparison. Now, we can make this stage feel more like a journey by placing Roman in time gently. Roman is in the phase where it has been assembled and is moving through preparation and testing toward launch. Testing is slow, quiet work. Instruments are checked, calibrated, and verified. Spacecraft systems are exercised and measured. This is not glamorous work, but it is the work that makes later science possible. You can picture it like a musical instrument being tuned before a concert. The tuning is not the concert, but without tuning, the concert cannot be true. So, when we say Roman will map voids, we are also saying something comforting about science. We are saying science is willing to wait. It is willing to validate. It is willing to build the measurement carefully so the conclusions do not have to shout. Now let's return to the voids again. Why does Roman's wide, deep, stable mapping matter so much for void science specifically? Because voids are defined relative to the average. You need to know what typical density looks like in your survey. You need to understand how your survey sees galaxies. You need to correct for selection effects for the fact that some kinds of galaxies are easier to detect than others, and that detection changes with distance. A strong survey mission is built around managing those effects. Uniform data makes it easier to model selection. Large area makes it easier to average down local fluctuations. Deep reach makes it possible to see enough tracers across a wide range of distances. All of this transforms emptiness from a vague word into a measurable object. Now let's pause and let your mind rest for a moment, because we have placed several important ideas on the table. Roman is a wide field survey telescope. Void science requires wide area and deep catalogs. Stability and repeatability are essential for reliable statistics. A large ensemble of galaxies makes underdense regions measurable. If you are drifting, you can let those statements float like soft lanterns. You do not need to hold them tightly. They will come back naturally. Now, we can add one more gentle layer that makes Roman's role feel even clearer. Cosmic voids are not only interesting because they are underdense. They are also interesting because they create a kind of geometry in the galaxy distribution. The universe expands. Distances between large structures change over time. When we measure patterns in the distribution of galaxies, we are indirectly measuring the scale of the universe at different epochs, different look-back times. Roman surveys are meant to observe enormous numbers of galaxies across a large volume. That means Roman's data can support multiple kinds of large-scale structure analyses, and voids can be one of those. So Roman is not a telescope that says, look at that one thing. Roman is a telescope that says, look at the pattern and let the pattern teach you. And that is exactly the voice you want for a science-heavy sleep narrative, because the pattern does not demand urgency. The pattern rewards patience. Now, as we begin to close this stage, it helps to set up a clean bridge to the next stage. In stage 1, we learned that voids are real measurable regions of the cosmic web, best understood as a population and not as a single dramatic object. In this stage, we learned why Roman is the right tool for turning that population into a strong measurement-wide field, deep mapping stable survey data, and enough galaxies to trace the structure. In the next stage, we will connect the measurement to the question: how does the statistics of emptiness tell us about the expansion of space? And why does that connect to dark energy? Not as a mysterious substance, and not as a headline, but as a behavior we can infer from the geometry of large-scale structure. Before we move on, let's place one final image simple enough to carry into sleep. Imagine Roman as a lantern lifted above a wide landscape at night. It is not trying to light up a single flower. It is trying to reveal the shape of the valley, the ridges where galaxies gather, the open hollows where they are rare, the gentle negative space that turns a scattered field of lights into a readable map. And in that map, the emptiest regions do not disappear. They become the measurement. When you are ready, We will follow that measurement into the quiet question behind it, the question of how the universe expands and what its emptiest spaces can tell us about the invisible rules guiding that expansion. In the first stage, we learn to see cosmic voids as real structures, not as nothingness. In the second stage, we met Roman as the kind of telescope that can map those structures across a wide, deep volume. Now, in this third stage, we connect the map to the meaning, not meaning in a poetic sense, meaning in the calm, technical sense that science uses, the sense in which a pattern carries information. This is where many explanations become loud because dark energy is often treated like a mystery box. Tonight, we will do the opposite. We will treat dark energy as a name for a measured behavior, and we will let voids be one of the ways that behavior can be tested. So let's begin with a simple anchor that you can hold lightly. The universe expands. That means the average distance between far apart galaxies increases with time. This is not the motion of galaxies through space like cars on a road. It is the stretching of space itself on large scales. And because light takes time to travel looking far away, also means looking back in time. When we map galaxies across distance, we are mapping the universe across different ages. In that sense, a large survey is a quiet time machine, not one that visits the past, but one that receives the past as light. Now, where do voids enter this story? Voids are tied to expansion because they are part of the geometry of large-scale structure. The cosmic web is a pattern that forms under the combined effects of expansion and gravity. And in our current best model, whatever drives the late-time acceleration of expansion. If you want a gentle image, think of a loaf of rising bread with raisins inside. As the bread rises, the raisins separate. But the bread also has internal structure because some parts are denser and some are airier. The air pockets are not separate from the loaf. They are part of the loaf's shape. In the universe, the voids are like the air pockets in the cosmic loaf. They have sizes and shapes that depend on the history of how the loaf expanded and how matter flowed. That is the basic connection. Now we can take one step deeper still in one calm layer. In dense regions, gravity pulls matter inward strongly. The physics becomes nonlinear and messy. In underdense regions, gravity still matters, but the intense collapsing behavior is less dominant. In a void, matter has already drained away toward the surrounding filaments and walls. That makes voids, in many analyses, a relatively clean environment for studying large-scale trends. Clean does not mean simple in every detail. Clean means the strongest signal can be less obscured by local complications, and in cosmology, the strongest signals often appear in statistics, not in single objects. So what are the statistics that people use? We will talk about 3 families of void measurements and keep each one to a single restful layer. First family. How many voids exist at different sizes? Imagine you have a map of a coastline and you measure the sizes of bays along the shore. Some bays are small. Some are large. The distribution of bay sizes tells you something about the history of erosion, about how the coastline formed. In the cosmic web, the distribution of void sizes tells you something about how structure formed under the rules of expansion and gravity. If a cosmological model predicts one distribution, and the measured distribution is different that is meaningful. And if the measured distribution matches that is also meaningful, it is a quiet yes, a soft constraint. Second family, the typical density profile of a void. A void is not a flat, empty bubble. Many voids have a structure where the center is the most underdense region, and the density rises toward the edge where the void meets the filaments and walls. If you stack many voids together and average them, you can build an average profile like a gentle bowl. The shape of that bowl can change with cosmic time, and it can depend on cosmological parameters. This is one reason surveys are so powerful. A single void might look irregular, but the average over many voids becomes smooth, and the average can be compared to theory. Third family, how voids relate to light. Bending through gravitational lensing. This one sounds counterintuitive at first because a void is underdense. You might expect an underdense region to have no lensing effect. But lensing is not only about high-density clusters. It is about mass distribution, including the fact that voids sit inside a larger pattern. The edges of voids and the surrounding structures can produce subtle lensing signatures when you average over many lines of sight. So a void can be studied by how it gently distorts background galaxies statistically in the same way you can detect a very weak current by watching many leaves drift over time. This lensing connection matters because lensing is sensitive to the total mass distribution, including dark matter. It gives a complementary perspective, not just where galaxies are, but how mass is arranged. Now you might notice that all of these measurements share a theme. They are not about a single dramatic picture. They are about patterns that remain when you combine many observations. That theme is perfectly matched to Roman survey design. Roman's wide and deep mapping is not only useful for finding voids, it is useful for making the statistics of voids precise. It increases the number of voids. It improves the uniformity of the galaxy map. It supports the calibration needed to trust the ensemble. And when you trust the ensemble, you can ask the cosmological question with more confidence. Now we can name dark energy in a way that stays grounded. In the standard cosmological model, the expansion of the universe is accelerating at late times. Dark energy is a name we give to whatever is responsible for that acceleration in the equations that best fit the data. In the simplest case, it behaves like a cosmological constant, a uniform energy density of space. In more complex cases, it could vary with time. The details are active research, but the key point for tonight is this. Dark energy is not introduced as a story. It is introduced as a label for a measured behavior, accelerated expansion. And because it is a measured behavior, it should leave multiple measurable signatures, not just in one data set, but across many. That is why cosmology values cross-checks. If void statistics support the same expansion history inferred from other probes, the model becomes more credible. If they differ, the difference is not drama. It is information. It is a sign that either the measurements need refinement or the model needs improvement, or both. This is how science stays calm. It does not demand certainty on the first pass. It tightens the net slowly. Now, to make this feel more concrete, without turning it into a lecture, let's walk through a quiet chain of inference. Step 1 map. galaxies across a large volume. Step 2. Identify underdense regions and characterize them as voids. Step 3. Measure void statistics such as size distribution, average profiles, and correlations. Step 4. Compare those statistics to predictions from cosmological models, including models with different expansion histories. Step 5. Accept what the data supports and label what remains uncertain. That is the method. Notice that nothing in that method requires a dramatic claim. The drama is replaced by the dignity of comparison. Now, there is one subtle point that helps the whole stage feel more trustworthy. When we talk about void statistics, we are always talking about how the measurement depends on what you choose as tracers and how you define a void. This might sound like a weakness, but it is actually a strength when handled properly, because it creates multiple internal checks. If your result is real, it should appear in a stable form across reasonable choices of definition and algorithm. It may shift a little, but the underlying trend should remain. If your result vanishes when you change a modest assumption, that is a sign the result was fragile. So the existence of multiple void-finding methods is not a problem to hide. It is a tool to use. It is a way of asking softly whether a conclusion is robust. Roman's large data set can support that robustness testing. The more data you have, the easier it is to explore definitions without losing statistical power. Now, we can place one more idea gently on the table because it makes the connection between voids and expansion feel more intuitive. Expansion sets the scale of the universe. If you stretch a pattern, the typical separations and sizes of features in that pattern can change. The cosmic web has characteristic scales, and those scales evolve. When you measure the distribution of large-scale features across distance, you are indirectly measuring how the scale factor of the universe has changed. Voids are part of that feature set, not in the sense that one void is a standard ruler all by itself, but in the sense that a population of voids measured consistently across cosmic time can trace changes in structure and expansion in a way that can be compared to other cosmological probes. This is why voids are described as complementary. They do not replace other methods. They add another angle of view, and when multiple angles agree, the picture becomes more stable. Now let's talk about lensing around voids one more time, because it is one of the most elegant connections for a sleep narrative. Lensing is the universe writing with gravity. It is the way mass shapes the paths of photons. We are used to hearing that clusters of galaxies create strong lensing bending light into arcs. Voids produce the opposite kind of effect, a subtler distortion that can be detected statistically. If you imagine space as a fabric, dense regions make deeper dimples. Voids are shallower regions surrounded by dimples. Light passing through the overall terrain is gently deflected in ways that can be averaged and measured. So by stacking the lensing signal around many voids, you can infer something about the mass distribution in and around those underdense regions. That matters because it connects the galaxy map to the total matter map, including dark matter. So voids can be probed in two parallel ways. One way is through where galaxies are missing in a statistical sense. Another way is through how background light is distorted in a statistical sense. When those two views line up, they reinforce each other. This kind of agreement is one of the most soothing forms of scientific confidence. not loud confidence, layered confidence. Now, because you wanted the channel to lean more towards science, we can add a careful calming note about what Roman changes in practice. Roman is expected to expand the scale of these measurements because it can survey wide fields with depth and uniformity. That means more galaxies in the catalog, more volume, more voids, better statistics, and better statistics do not guarantee a surprising conclusion. They guarantee something quieter and more valuable. They guarantee narrower uncertainty. In cosmology, narrower uncertainty is a form of progress that does not need fireworks. It is like adjusting a lens until the image is just a little sharper. The world is the same world, but your description becomes more precise. Now, if your mind drifts, here is a short, sleep-friendly summary of this stage shaped as a few calm statements. The universe expands, and we see different cosmic times by looking to different distances. Cosmic voids are underdense regions shaped by the same expansion and gravity that shape the rest of the cosmic web. Voids can be studied statistically through their sizes, profiles, and correlations, and also through weak gravitational lensing. Those statistics can be compared to cosmological models to test expansion history and the growth of structure. Dark energy, in this context, is a name for the behavior of late-time acceleration that models are trying to explain. And voids are one way to test that behavior. You do not need to carry more than that. Now, we will place one last gentle image to close this stage and prepare the ground for the final stage. Imagine Roman making a map of the night sky that is not a collection of pictures, but a collection of relationships, where galaxies are common, where they are rare, how the rare regions cluster and stretch and change across distance. In that map, emptiness is not ignored. It is measured, and when emptiness is measured across a large enough volume, it becomes a quiet ruler. Not a ruler you hold in your hand, but a ruler made of statistics and consistency. A ruler that helps us describe how the universe has been growing slowly and steadily for billions of years. In the next stage, we will let the method become even calmer. We will talk about uncertainty as a feature, not a flaw. We will talk about why cross-checking matters and why Roman's greatest gift may be the gentle tightening of what we can say without forcing us to say more than the data allows. For tonight, it is enough to feel the main idea settle. The emptiest places can carry some of the clearest information. A wide survey can turn that information into a measurement. And a measurement repeated across time and distance can tell us how the universe expands without needing the universe to shout. By now, you have the core picture. Voids are real structures in the cosmic web defined by being underdense rather than by being empty. Roman is a wide survey telescope designed to map large areas deeply and consistently. And the statistics of voids can connect in a testable way to the expansion history of the universe and to the growth of structure. So in this final stage, we do something that is both scientific and restful. We slow down and place boundaries. We remind the mind what science is actually trying to do here and what it is not trying to do. Science is not trying to win an argument in a single night. Science is not trying to generate certainty out of thin air. Science is trying to reduce uncertainty responsibly and to make predictions that can be tested. In cosmology, that reduction of uncertainty is the real work. It is the quiet work, and it happens in layers. A survey mission like Roman does not promise a single dramatic conclusion. It promises a better map, a larger sample, a cleaner measurement, a narrower range of what can be true. That might sound modest, but in science, modest narrowing is often how understanding deepens. Now, let's name one principle that protects both good cosmology and a calm nervous system. A result is stronger when it survives changes in method. If you measure a pattern one way and it appears that is interesting, if you measure it another reasonable way and it still appears that is stronger, if it appears across multiple independent data sets and different techniques, it becomes stronger still. This is why void science emphasizes robustness. Voids can be defined in more than one way. Galaxies can be selected in more than one way. Distances can be estimated with different methods. Analysis pipelines can vary. Each of these variations is not a threat. It is a test. And when a conclusion remains stable across those tests, it deserves trust. Roman's contribution in this sense is not only the number of galaxies, it is the ability to perform these robustness tests without losing statistical power. The data set is large enough that you can try multiple definitions and still have enough voids for meaningful results. This is what good data buys you. It buys you the freedom to check yourself. Now, there is another principle that belongs here, and it is about cross-checking with other cosmological probes. If you rely on only one measurement channel, you risk mistaking a systematic bias for a cosmic truth. But if multiple channels point to the same expansion history, the likelihood of a shared mistake shrinks. This is why modern cosmology is built as a network of probes. Supernovae trace the distance redshift relation in a particular way. Large-scale structure analyses trace the distribution of galaxies in the geometry of clustering. Weak lensing traces the mass distribution through subtle distortions in shapes. And voids add a complementary angle because underdense regions can respond differently to certain effects and can be cleaner in some respects. When these probes agree, the model becomes more credible. When they disagree, the disagreement is not doom. It is a clue. It tells scientists where to look more carefully. It tells them which assumptions may need refinement and which measurements need deeper calibration. This is the emotional difference between good science and noisy speculation. Speculation treats disagreement as a fight. Science treats disagreement as a map of where to work next. So Roman's role can be framed in a very calm way. Roman helps improve the map. A better map makes void statistics more precise. More precise void statistics tighten constraints on expansion history. And those constraints can be compared with other probes to test cosmological models. Notice how little drama that requires. Now, because you asked for science heavy, we can be honest about the kinds of uncertainties that remain and still keep the tone soft. There are uncertainties in how galaxies trace matter. Galaxies are not perfect markers of the total mass field. There are uncertainties in how distances are estimated, especially at large scales. There are uncertainties in selection effects, because surveys detect some objects more easily than others. There are uncertainties in defining void boundaries, because different algorithms carve the density field differently. But none of these are reasons to despair. They are reasons to measure carefully. And careful measurement is exactly what survey missions are built to support. Now, let's turn that into a sleep-friendly metaphor you can carry. Imagine you are drawing a coastline by hand and pencil in the dim light of evening. The first pass is rough. The line wobbles. Then you walk the shore again. The line becomes less wobbly. You walk again and again. Each pass does not change the coastline. It changes your drawing. That is what cosmological surveys do. The universe is the coastline. The survey is the repeated walk. The science is the line becoming steadier. Roman is a mission designed to make that line steadier. Now we can place the gentle CTA here as a brief quiet pause and then return to calm immediately afterward. If you would like to continue traveling through these wide, quiet experiments in modern astronomy, you can subscribe to Quiet Science Journeys. We will follow Roman as it moves from preparation toward launch, and as its maps begin to shape a clearer picture of the universe's largest structures. And for tonight, you can simply let that be a small bookmark, nothing more. Now, let the energy settle again. We will end this stage with one final discipline that is especially soothing, the discipline of not needing a final answer too soon. Dark energy is a name attached to a set of measurements that suggest accelerated expansion. The simplest model fits it as a constant. Other models allow it to change with time. There are also ways to phrase the question in terms of gravity itself on large scales. Cosmology is not a single solved story. It is a field of models tested against data. Roman will not end that field overnight. Roman will refine it, and refinement is a gentle kind of progress. It is progress that does not require a single decisive moment. It is progress that can happen through many small improvements in mapping calibration and statistical power. So if your mind asks Will Roman, tell us what dark energy is, a calmer and more accurate question might be this: will Roman reduce the space of possibilities? Will Roman make certain models harder to maintain? Will Roman make some explanations more consistent than others? That is how cosmology moves forward. By narrowing the room, not by slamming a door. Now let's close stage 4 with a few calm statements, like placing folded cloth into a drawer. First voids are measured statistically, so reliability comes from large samples and careful definitions. Second, a result is stronger when it remains stable across reasonable changes in method. Third, Roman's wide and deep surveys are designed to support that stability and reduce uncertainty. Fourth, cosmology becomes more trustworthy when multiple independent probes converge and disagreements become guides rather than alarms. And finally, the purpose of Roman in this story is not to create a headline, but to tighten the measurement. Now, we are ready to let the whole journey soften into its closing. A cosmic web threaded with bright filaments, a wide, quiet hollow between those threads, a telescope that maps the pattern patiently, and a science that becomes kinder to the mind as it learns to say, with growing precision, this is what the data supports, and this is what can rest for now. In the closing, we will release the details and keep only the feeling that even the emptiest places can be meaningful, that careful measurement can be calm, and that for this moment, This gentle understanding is enough. We have reached the end of tonight's journey, and you do not need to carry any more details forward. The numbers, the statistics, the careful ways of defining a void, the slow logic of surveys and cross checks, they can all rest now, like instruments placed gently back into their cases. What remains is simpler, a universe shaped like a web, bright threads, where galaxies gather, and wide hollows between the threads, places that feel quiet, not because they are empty, but because they are sparse. Places where the large-scale pattern can be read with less distraction. And somewhere in that story, a telescope designed not for a single dramatic close-up, but for patient mapping. Roman, moving slowly across large pieces of sky like a wide lantern, returning again and again, not to create a headline, but to reduce uncertainty, to make the map steadier, to let the universe speak in the calm language of patterns that survive repetition. Tonight, you met an idea that sounds almost backwards at first. That absence can be measured. That emptiness can leave a signature. That the quietest regions can carry some of the clearest information, not because they are magical, but because they are less crowded with complications. You do not need to decide what dark energy is in a final sense. You do not need to solve cosmology in a single night. It is enough to know what science is doing here, making a wider map, testing multiple methods, comparing independent probes, and narrowing the room of possibilities slowly, carefully, without rushing the mind. So now you can let the web soften in your imagination. Let the bright filaments fade to a gentle glow. Let the wide voids feel like calm open water between islands of light. Let the map become less like data and more like a quiet landscape you are allowed to leave behind. Outside this story, the universe continues its slow expansion, indifferent to our attention. But inside this story, attention becomes a kind of peace, not because it gives perfect answers, but because it gives the mind a method and a boundary, and a way to set down what it does not need to hold. If sleep is already close, you do not need to reach for it. You can simply allow it. Let the last image be simple: a wide lantern moving slowly, a dark web of galaxies, a quiet hollow between its threads, and a gentle understanding that even the emptiest places can be meaningful when we learn how to measure them. For this moment, this is enough.